All right, so let's introduce this summation notation. So let's let A1, A sub 1, A sub 2, A sub 3, blah, 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 A sub n be any list of real numbers, right? Some ordered list. This notation, right, the sum of the A sub I starting at 1 and stopping at n just means to add all of these numbers up. So this is just a shorthand notation for this, right? It's a compact notation. Instead of using I as my counter, I could have used J, or I could have used L, or I could have used any symbol that I want. So all three of these things mean the same thing. You just want to make sure that these two variables match. So for example, this is not the same thing as the sum I equals 1 up to n of A sub j. In this case, this thing is just a constant, and we'll see how to deal with those later, right? So this is not the same thing as either one of these three. Okay, instead of starting at 1, we could start at any number. So here, if we start at 3, then this notation means the sum of the A sub I from I equals 3 up to I equals n. So that's A3 plus A4 plus A5, blah, 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 plus A sub n. And so we just need, in this case, we need n to be bigger than or equal to 3 in order for this thing to make sense. Okay, here's a quick example. So if A sub I is given by I minus 1 squared, so here's basically a function, right? So A sub I is a function of I, and this tells us exactly what each of these numbers should be, right? And again, we always think of these indices as being integers. So usually starting at 0. So if you like, A0 would be 1, A1 would be 0, A2 would be 1 squared, so that's going to be a 1. What's A3 going to be? So 3 minus 1, that's 2. 2 squared is equal to 4, blah, blah, blah. So that's what the list, right? This is what the list would look like. 1, 0, 1, 4, and I think the next one would be 9, so on and so forth. So we want to find the sum of these A sub i's starting at 2 and stopping at 5. So here's the notation. Here's what it means, right? The sum of the A sub I starting at 2 and stopping at 5. That means A2 plus A3 plus A4 plus A5. And now we just need to say what each of these things means. Well, A sub I is I minus 1 squared, so A2 is 2 minus 1 squared. Again, we did some of those up here. Right, 2 minus 1 squared, 3 minus 1 squared, plus 4 minus 1 squared, plus 5 minus 1 squared. And so you just work all this out, right? 1 squared plus 2 squared plus 3 squared plus 4 squared, that's going to be 30. So that would be a good final answer for this thing. Okay, here's a theorem, right, that we will need. This first one says that the summation notation is linear. In other words, it goes through sums, it goes through constant multiples, and then this one here just says, well, if I add up the same number to itself n times, I just get n times that number, which seems reasonable. And then this thing says that if I go from 1 to n of A sub I, well, if I subtract 1 from my counters, right, so to go from 0 to n minus 1, that means I should add 1 to the index here. So if I start at 1, then the first number is going to be A sub 1, and the last one's going to be A sub n. Well, the same thing is going to happen here. If I start at 0, the first thing is going to be A sub 1, and then A sub n minus 1 plus 1 is going to give me A sub n. So whatever I subtract from here, I need to add to here. Sorry, this should be I minus 1. Right, whatever I subtract from here, I should add here and vice versa. Okay, maybe let's just take a look at the proof of one of these things just so you can get more comfortable with this notation. All right, so here's a quick proof of why item 1 works, right? That the summation notation goes through sums, and you can also say that it goes through differences too. I'll leave that as an exercise for you to check, replacing the addition sign here with subtraction. So the sum of AI plus BI, what does that mean? Well, it means A1 plus B1 plus A2 plus B2 plus blah, 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 plus AN plus BN, right? So by definition, this thing is the same thing as all of this. But we know that addition is commutative. In other words, we know that x plus y is the same thing as y plus x. So you can write down addition in any order that you want, and it's not going to change the value of the expression. So I can write all of the a's next to each other. Right, so this is the same thing as A1 plus A2 plus blah, blah, blah plus A sub n plus B1 plus B2 plus blah, blah, blah plus B sub n. And by definition, this first summand is just this thing, right, the summation notation, and the second summand is just this thing. Really, there is also the associative property thrown in here too, but you see how this works. Okay.